So now we will enter the second part where we are going to talk about the use of divide and conquer technique to improve the sorting algorithm. So there are two very well-known sorting algorithms that apply this kind of principle: quick sort and the merge sort. And our focus today will be the merge sort. The basic idea of the merge sort is you start from basically the smallest possible unit, which is a single element. Then you try to merge them into gradually larger and larger cases. So the size of 1 merge into size of 2, size of 2 merge into size of 4, size of 4 be merged into size of 8, so on and so forth. So we'll look at first the iterated version of merge sort. And next week, when we introduce recursion as one way to supplement our algorithm design, then we will see how the same idea can be applied in turning the merge sort into a recursive function. All right, so basic idea that we just described is a very bottom-up idea. We can visualize that a little bit. We use the smaller building block and gradually build larger and larger semi-completed solution. Here, this is one example. Original input is a particular list that contains 8 different elements. And then the smallest possible unit will be a size of 1. We merge them up. Once we start from size 1, we merge 2 size 1 into size 2. Then again, from size 2, we merge it with the nearby other size 2 list, sublist into size 4. And the final step, we merge 2 size 4 lists into 1 size 8 list. And that finished the process. So this is a very quick process about like how visualization showing that how merge sort actually work. If you want to actually see it in action, again, you can open up the COR-IS notebook. You can execute the portion, the specific section on merge sort. So what you should know over here when you begin to look at the code is that we use GS to represent the group size. You start from the smallest possible unit, which is 1, but you will double that every time, right? You double it because every time that you execute the merging process, you will merge 2 units into 1 larger unit, right? And this is actually where the merge source merge come from. You merge 2 smaller, fully sorted unit into 1 unit, right? So let's see how it works. The highest level of the function design, again, over here, we adopt multiple helper function so we can keep our logic simple. The highest level illustrates the skeleton of our algorithm design. We start with the group size 1, and then we are given this particular list A, originally is not sorted. So this GS will just keep increasing until you go above the length of list, which is the n, right? And then you try to merge the groups by specifying the GS. Okay, so again over here you can see very simple. The major thing we'd like to highlight is that we will specify a GS starting from 1, but then we will use the merge group function to execute the actual step of merging 2 groups of size GS into 1 group that's with the size of 2 times GS. So you can see if you want to estimate the numbers of times that it take you to execute this particular while loop over here, you just recognize the fact that because GS is being multiplied by 2 every time, essentially what we are looking for is this particular case step such that after you multiply you double the group size by 2 k times, eventually you should go either equal n or go above n, right? So very similar to the previous case of binary search, right? So we have this relationship. We want to find the numbers of steps. So k is the numbers of steps that we are looking for. Again, you take log base 2 function on both sides, k drop down. So the numbers of steps that will require you to double the group size until eventually you go equal or above the list size n will be log 2n, right? So this is at the highest level how many times this particular while loop will execute. So now we progress to the next level, which is how groups are being merged. Right, so this is the merge function. Here you can see that we try to again use the index I to progress through the whole array, whole list. Right, starting from 0, this is the very first element, and then J actually over here indicates the other end. Right, so if you want to visualize the execution of this, it's something like this. Right, so you process one subregion at a time. This is I and this is J, right? And the width of this will be 2 times GS, right? Which means that inside this merged length, you have A1, you have A2. A1 will have the size of GS. A2 will also have the size of GS. And here you can see that this is the lower index of A1. And this is the upper index, right? So this particular syntax basically say that the largest upper index of A1 is actually this number minus 1. So the upper index will be I plus GS, but minus 1, right? So for A2, you will be next index. This is your lower index. And this is the one more than your upper index. So your upper index will again be I plus 2 times GS, but minus 1. Okay, so after you have you have obtained the first list, and you get the second list, which is actually extracted from the full list. You use this function, merge function, to merge them into a larger piece, a particular array, a particular list, just like the diagram that we show over here, right? That is composed of the merge result from A1 and A2. After you are done, you move on, you increase your I index, which is the lower bound, the beginning of this merged sublist, by the size of 2GS. So if you count it, again over here, if you want to count the effort, if the size of the list is n, and then you want to find the relationship if the current group size is GS. In the case where your GS equals 2, your n equals 8, then there will be 4 groups. And then these 4 groups are the GS group, right? But in this merge group function, we are merging 2 GS equals to 2 subgroups into one merge group, right? So in other words, you have 4 groups, but you only have 2 pair of groups that can be merged. So the numbers of steps of this particular while loop essentially equals the numbers of pairs, right? Because every time your I is increased by 2 times GS. So the total numbers of times that you're going to execute this loop will be n divided by 2 GS, right? So again, we accumulate this result incrementally. Those will be important facts that we are going to utilize later when we analyze the complexity of merge sort. Right, so now the critical part about how merge happen is in the third function, which is over here, right? Let's see how it works. This is graphically how it works. So let's say for now, right? So this is like the head of your list, right? We label it this way so it's easier to see. So it means that the order is actually happen in this direction, right? So you have the smallest value all the way until the largest value to this left hand side. And then what you do is that you're going to compare the first element. Let's say for example you have 1 and 3, right? That's as an example. You pick whichever element that's the smaller, right? So you pick 1, 1 from A1, you goes into the merge list. You cross it over. Let's say the second element is 2. Then again, you compare the head element, right, which is 2 against 3. Again, the smaller element will go down. You continue this process until all the element is being placed inside the merged list, right? So originally A1 is sorted, right? And then A2 is also sorted. but then you use this merge function to produce a list that's fully sorted by performing like one comparison at a time. Every time you finish one comparison, one element will be put into the place. So if you do the analysis as a result, let me probably just erase this so you actually see it. So if you do the analysis, in the worst case, to place each and every element, you need one comparison, except the final one, right? Because the final element has nobody to compare to. So in the worst case, the total numbers of elements that you need to place is the total, a total comparison you need to perform will be the total element 2GS minus 1. Okay, so again, this is the lowest level of operation. Later, we will utilize that, again, as mentioned, to perform complexity analysis. So as an example, if you want to demonstrate how it works, we can use this two different scenarios to indicate that. So we have 1, 2, 3, 4. We have 5, 6, 7, 8. So we can probably just write it following the order. So if we follow write the order this way, it means that the merged list need to go this side, right? This is the merged list. I think that's easier perspective, right? So we compare the first element of both. 1 is actually smaller, so it's being crossed out. You write it down over here. And then you compare 5 against 2. Again, 2 is smaller, so go down. You compare 5 against 3. Again, 3 is smaller. And then you compare 5 against 4, right? After you have finished this, you will see that actually there's no comparison needed. All you need to do is copy the remaining element in, right? You have 5, 6, 7, 8, right? So this is the first example about how merge function will work. The second example is very similar. You have 1, 3, 5, 7, 2, 4, 6, 8, right? You want to merge it following very similar principle. The first one, the first element, compare against each other. 1 goes into the merge list, and then 2 against 3. So 2 goes into the merge list. 3 against 4, 3 goes in, and then you have 4, right? And then you have 5, and then 6 compared to 7, 6 go in. 7 compared to 8, 7 goes in. And this is the final element. It goes into the merge list without comparison. So in this case, you can see that the total numbers of comparison will be 7, right, which is the numbers of element 8 minus 1. In this case, you only need to perform like 1, 2, 3, 4, right? 4 different comparison. Then you will be left with one empty sublist. So the remaining list will just be inserted accordingly without any comparison, right? So this is how in terms of the numbers of comparison, this is probably the best case scenario. This is the worst case scenario. Okay, so I think this is how it works. So now we can look at the actual implementation. So this code basically try to simultaneously iterate through A1 and A2. We use I and J to represent the index that's inside A1 and A2. RET, this is representing the return variable. That is containing all the merged component, right? So if you look at the first condition over here, we look at 2 different conditions, and as long as one of the conditions is true, we will proceed. The first condition says that you have at least one element in A1. The second element says that you have at least one element in A2. So basically, it means that you still have work to do. And the second condition over here inside this if statement is that if your J already reached the end, it means that you have no more element in A2. Then the second part will not be evaluated, right? You don't need to do anything, right? You can directly just append this element from A1 to the return variable because you have no element in A2 you need to compare to. But if you do have element, what you do is that you're going to, if there's any element left in A1, you're going to compare A1's pointed to by I, the current index I, and A2 pointed to by the current index J. If A1 is smaller, you're going to append A1, right? So here you can see that both condition, either A2 has run out of the component, or I mean you have element, if that's not the case, and then you check that you actually have element in A1, and then A1's element at position I is smaller than A2's element at position J. That is the case where you are going to insert A1I into the return list, right? And then because you get you try to process element in A1, so you increase I's index by 1. Then you do, I mean, if this both conditions are not true, it basically means that then the only feasible list that you should get element from will be from A2, right? So in the second case, you get element from A2, so you increase the counter J by 1. All right, so that is basically how the merge work. I mean, if you want the practice, you can see the previous page as well. All right, and I would encourage definitely you try to try your hand on like at least this one cases or two cases that we have mentioned in the previous slide. Okay, so now nothing beats the actual tracing of the program. If you really want to understand how the algorithm work, use a very small example, 8 different element, and try to see how the merge actually work. And here are a couple of the key spot you should pay attention to. How the merge function work, right? You try to observe the progression of both I and J, and then you see how the original range of Aij get overwritten by the merged result, which should be sorted. Right? Originally, you have a very clear division of A1 and A2, but after you execute this merge function, A1, A2's range should become fully sorted. Right? So you'll be provided to overwrite the region from I to J. Right? So try to observe how this happened, and of course, this is the return function that's within the merge function. Right? You try to see how this particular element is passed out and interact with this particular function merge group, right? So go through this process, try a couple different instances, make sure that you are comfortable with the tracing of the program, fully understand these 3 different tiers of the merge sort operation, right? So that will help you with the understanding of the code, right? So now we have the implementation. We actually break down the step, the numbers of count at different level. So now we can combine all these numbers that we have come up with along the way to conduct the complexity analysis, right? So these are all the critical numbers that we have mentioned previously. At the highest level, the numbers of pairs that to be merged is dependent on the GS, right? The current GS suppose is 1. It basically means that a numbers of pairs will be reflected at the higher level. All right, so this here you have 8 element. Let's say your GS is 1. It basically means that you have 4 pair that to be merged, right? And then numbers of move that will be required to merge a pair of the size 2 times GS will be 2 times of GS, right? I mean, strictly speaking, is 2 times GS minus 1. But for simplicity, just drop this minus 1, right? So it will be 2 times GS. In other words, if you are looking at a particular level, let's say GS equals 1 or GS equals 2, the total numbers of move or comparison that will be necessary will be n divided by 2GS, which represent numbers of pairs, and the numbers of move or comparison, right? So 2 times GS. So if you multiply that, you'll find out that actually for each and every level, total numbers of move stay constant, doesn't really change. It's always n, regardless of the GS, right? So I think this is the first crucial number. Every level is actually n. So the major, here comes the most important part. The major saving as a result is actually the numbers of times it take you to go from GS1 to eventual the full array size, full list size of n. So this number we have talked about before, right? So if you keep increasing, keep doubling the size of GS by a factor of 2 every time, it takes you log 2n levels to go from the group size of 1 to group size of n, which means that if your n equals 8, it only take you 3 levels to reach the fully sorted size of n, right? So every level, right? So you can see that this GS go from 1 to 2, 2 to 4, and then 4 to 8, right? The last level is not written down over here, but we should have a level, I mean, the final result, which is 8 element, right? So it only take you 3 different operations, 3 multiplication, then you can go from 1 to 8. And that is a log function. And every level we said, right, only takes it will take a fixed number of operation, which is n. So the total numbers of complexity as a result will be n times log n. And that is a great improvement, right? What we have. It's a great improvement because once you plot it out, both the insertion sort, which is this line over here, and the merge sort, you see that when the n number is small, they seem to be pretty close. But once you reach a decent size, the difference may be huge, right? While the merge sort is still in the hundreds, the insertion sort is already in the thousands. That's in terms of numbers of operation. So huge differences. And let alone, I mean, this is only 100. So now imagine if you have, let's say, a million, right? So the difference will be even greater. Okay, so that is the reason why merge sort is so efficient, right? You replace one of the n with log n. And as a result, the curve that you see will be much closer to the linear line. Not exactly linear, but not too much from it, right? So let's, just like before, just like the insertion sort case, let's look at these 2 different lists, and we will now practice both the insertion sort and the merge sort, right? And then we try to see that if you are going to execute a sort, there's 2 different sorting algorithms, which particular method will incur more comparison, right? So you see that we already know the complexity, right? Merge sort is actually, in terms of complexity, is better than the insertion sort. But in terms of the actual numbers of comparison, it's hard to say, right? So that's why we give you these 2 very specific examples. Try to quantify exactly how many operations will be needed by both sorting methods.